Okay, so the question where we left off, we're trying to find what's the coefficient of friction of this ground that the kids slide across. So the question was, there's a 50-kilogram kid at the top of a slide, and he begins to slide down, and he doesn't notice a 40-kilogram kid sitting at the bottom. So when this 50-kilogram kid gets to the bottom, they collide. And when they collide, they become entangled. There's a mess of arms and legs and body parts. And they go sliding across the playground for 10 meters. And the question is, what must be the coefficient of friction of the playground if they eventually come to stop 10 meters later? So the key in these questions is to pick out the different parts. So one part is a change in height. One part is a collision. And one part is when they slide across the playground. So this change in height results in a change in speed. And so this, you have to use the energy, the conservation of mechanical energy equation. This is a collision. And always, always, always for a collision, you use conservation of momentum. And then here, as they slide across the playground, again, there's a change in speed. So change in speed, no collision, use energy. So there's three parts to this question. And the key is they're connected. Because the speed of the buddy at the bottom of the slide, at the end of the energy component, becomes his initial speed going into the collision. And then the speed with which they combine come out of the collision becomes the initial speed with which they slide across the playground. Okay, so the parts are connected. So in the last video, we had found the speed of the buddy when he got to the bottom of the slide. So rather than redo it with exactly the same numbers again, his speed when he got to the bottom that we had found, so we had used energy here. Number one was energy, and we did it previously. So see previous video. And in the previous video, we had found his final speed to be 14.007 meters per second. And so now we go into the collision, and that's momentum. So conservation of momentum is m1v1 initial plus m2v2 initial is equal to m1v1 final plus m2v2 final. Now, two things. It's sad here, but unfortunately these collisions, when we're doing the combined energy and momentum questions, they'll always only be one-dimensional. So you won't have to do x and y. You won't have to do this m1v1 initial x and then do it again in the y. Buddy number two is in moving initially, and finally they're combined. So you could write this as m1 plus m2 v final. Okay, so it'll be m1 v1 initial equals m1 plus m2 times v final. So the v final from the first part becomes this dude's v initial, and we're looking for the new final. So the new final will just be m1 plus m2, no, lie, it'll be m1 v1 initial divided by m1 plus m2. Okay, so m1, the guy at the top of the slide, is 1, so he's 50 kilograms. And we had found in the previous question that his speed was 14.007 meters per second. And we're going to divide that by 50 kilograms plus 40 kilograms. And we're going to find that after the collision, the two of them together go flying off at a speed of 7.7817, so I'm going to say 82 meters per second. So that's the speed at the end of the collision, at the end of the momentum. So now we move to the next part, which is energy again. So step 3, you write down your big energy equation again. 1/2 mv initial squared, mg h initial, 1/2 kx initial squared equals 1/2 mv final squared, mgh final 1/2 kx final squared plus E lost. Okay? So initially, when they go careening across the playground, do they have a speed? Yes. Do they have a height? Nope, they're on the ground. There is no spring. At the end, when they finally come to a stop, do they have a speed? Well, the key word there is stop. There's still no height, there's still no spring, but there is an E lost. So this time, it's 1/2 mv initial squared equals E lost. And so we have to remember what we said E lost was equal to. E lost is equal to the work done by friction. And work done is F delta D cos theta. So it's going to be 1/2 mv initial squared equals F, which is friction, delta D cos theta. Okay? What is F? Well, it's on a straight level surface, so friction should be mu Fn delta D. And really, it's going to be negative because it's opposing motion, but this then is going to also be the cos of 180 because they're in opposite directions. So the two negatives will cancel each other out. And on a level surface, we know that Fn is just mg. So mu mg delta D, my negative and my 180 are gone. On this side, 1/2 mv initial squared. So what is the m on this side? It's the mass of the two objects together after they collided. What is the m on the other side? It's the mass of the two objects together after they've collided. So the m's cancel. What is the velocity? The initial velocity with which they start across the playground is the final that they had after the collision. It's this 7.782 that we found. And we're looking for mu, so divide both sides by g delta d. So we'll have mu is equal to 1/2 v squared over g delta d. 1/2 7.782 meters per second squared over 9.81 meters per second squared. And I think I said 10 meters. May as well let them go for a good ride, right? So square your 7.782 divided by 9, so 50, 25, oh, I can't do that in my head. 7.782, and so now mine's going to be rounded. Okay, sorry about that. Squared times 0.5 divided by 98.1. And so they end up having a coefficient of friction of 0.308. I have 6.6, but I know that's off a little bit because I rounded my speed. Okay? Get the idea? So the trick is draw the picture and then figure out which parts change in energy, which part is momentum. So the collisions are always momentum. Any change in height, change in speed will always be energy. The final speed of one section becomes the initial speed of the next section. So suggested questions to follow up on these is on page 524, numbers 41 to 43. Okay? 524, 41 to 43. All right, give them a shot. Thanks.